So I'll be focusing our attention on the biomechanics of knee joint, okay, in this class. So apart from just few slides, I will be also referring to the book that has been uploaded for all of you, Nordin and Frankel book on basic biomechanics of the musculoskeletal system. Now, as you already have seen, that the knee joint is consisted of mainly 4 bones. Okay, so there are 2 stocky bones, which is the femur and the tibia. Apart from that, we have the kneecap or the patella, and then we have the fibula. Okay. Now, the primary joint that the knee joint, as we all know, we call it knee joint, is the tibiofemoral joint. But there is also the patellofemoral joint, which contributes to the movement of this joint. Okay. Now, as you can see here, I will just put the pointer. So we have the distal part of the femur with the 2 condyles. So this is basically the lateral condyle. This is the medial condyle. So this distal part of the femur articulates with the proximal part of the tibia to form this knee joint. Okay. From the front, on the anterior side, there is a laminar type of bone, which is known as the patella. And this patella is pressed into from the front by ligaments and tendons to form the patellofemoral joint. Okay. As you can also see that the cartilage, the presence of cartilage covering the ends of the bone. Okay, so we have cartilage cover at the distal part of the femur. The cartilage also is there in the tibia, which you cannot see here. It is called the articular cartilage or the hyaline cartilage. Apart from the cartilage, especially in the knee joint, there is the presence of another soft tissue, which is known as the meniscus. Okay, so if you can see here in this picture, this is the medial meniscus, this is the lateral meniscus. Okay, so in this picture, of course, this is the lateral meniscus. So this is the lateral side where the fibula is attached. So this is the lateral meniscus, and this is the medial meniscus. Now, this meniscus is basically a fibrocartilaginous disc. So it is a soft tissue fibrocartilage type, and it is actually seated between these 2 bones. Okay, so you can see very well, very clearly, the sort of bowl type, white bowl type meniscus in between the femur and the tibia. Now, I have discussed earlier about the arrangements, how this knee joint is held together stably. It is the stability of the knee joint is maintained by the ligaments. So the major ligaments that are present in the knee joint are the collateral ligaments on the two sides. So you have the lateral collateral ligament and the medial collateral ligaments on the two sides. I have also shown you the models of that. And you have the two very important crisscrossing ligament, and that is the posterior cruciate ligament and the anterior cruciate ligament. And this is marked very nicely, very clearly in red color in this lower picture. Okay, so you have ACL and PCL crisscrossing the knee joint. So together, these with the collateral ligament and the cruciate ligaments, the stability of the knee joint is mostly ensured. However, there is the important contribution of the patella that I will be discussing a little later. Now, let us first discuss about the meniscus. So, meniscus is basically a fibrocartilaginous disc, and it has specific function, out of which blood supply and a mechanism sort of it really, if you look into the individual functions, it shock absorber, it acts as a shock absorber in the whole structure. So it is not only acting as a shock absorber, but it also actually distributes the forces in a more even manner throughout this region, throughout the articular zone. And that this weight distribution is primarily because it adds congruency to the joint. So once you put these sort of congruent structures within these joint spaces, it actually distributes the load more evenly throughout the contact surfaces. So it decreases friction between the tibia and femur, and it also acts as a shock absorber. Apart from that, it also supplies blood to each and every part, and it is prone to also injury. There are several injuries associated with the meniscus because it is, at the end of the day, it's a soft tissue. Okay, the meniscus actually displaces within the joint during different movements, and I will sort of explain you from the textbook that how these things happen. If you refer to the book. So basically, just a moment, I'm looking to, so this is page 177, okay? So I will open the book. It's just a moment. Yeah. So can everybody see the book? It's too slow. Really slow. Need to go to page 177. Yeah. So this is typically the structure of this is typically the structure of the knee joint, as you can see here. So you can easily refer to this book and get hold of the structure of the knee joint. Now, the motions of the knee joint are primarily flexion and extension. Okay, but we still have certain specific motions which I will discuss. So you can see that the knee flexion and extension, when you flex the knee, you actually bend the knee. The opposite movement is extension. So flexion extensions are just opposite movements. I'll come to this slide later on, but let me just oops, no, this is not I want. So if I try to define the movements about the different axes, primarily for describing motions in the knee joint, we describe the motions along two planes, about two planes. One is the frontal plane. You can see the frontal plane. So this is marked here. Oops. Why this is not pointing? It's no problem. So you can see the frontal plane, and the other plane is the sagittal plane, which is normal to this frontal plane. We mostly describe motions in these two. There has been a lot of research in mathematically quantifying the motions in the knee joint, but it has been found that these two planes are sufficient to describe the motions, but the motions cannot be described. I mean, the transverse plane, which is cross-sectional plane, that is not of too much utility in describing motions of the knee joint. So primarily, the motions of the knee joint are based on sagittal plane and frontal plane. Okay. Now, if we look into the other figure, we can see that how these motions are being executed. So we have flexion extension to opposite motion. We have some internal rotation and external rotation, but these are very restricted movements. The most free movement of the knee joint is in flexion and extension. So the internal and external rotations and the sort of anterior and posterior rotations in form of varus valgus rotations are to a lesser degree in case of the knee joint. Now, if I like to say more about the tibiofemoral joint, So this is basically the range of motions of the knee flexion extension as you execute a walking cycle or a gait cycle. So maybe from 0, 20%, 40%, 60%, 80%, 100%. So this is an entire gait cycle. During this gait cycle, the degree of flexion or extension, okay, is plotted. The variation of the degree of extension, flexion, extension is plotted with respect to the percentage of the cycle, and you can see here that it has the maximum flexion to about, say, 90-degree flexion already during the gait cycle. Okay. Now, one important aspect of measuring the motions of the knee joint is locating the instantaneous center of rotation. Now, what is this instantaneous center of rotation? And how do we find it? Now, as you already have seen, perhaps you have noticed in while you were studying gait analysis, or when I explained you, that we need to find out forces and moments within a musculoskeletal system. Say we can take a limb segment, we first need to do a static analysis. So based on the weight, the angles created due to the posture, and the line of action of the muscles, we need to also locate the joint center about which we are calculating the moments. Okay, so calculation of the moments become very important because that can be later related to the torque applied. So in case of a dynamic analysis, we are more interested in the angular acceleration as well as the moment of mass, moment of inertia. So that will create a moment or torque, and this moment and torque is related to the joint moment or torque created at each and every joint. Okay. Now, when we actually calculate this moment, the moment arm or the lever arm, as I explained to you in my earlier lecture, becomes extremely important. So locating the joint center about which these rotations are taking place is very vital in the whole calculations. Now, there was another figure here. Just a moment. That figure may be more easier for you to understand because this is a scan. I go to this figure, yes, here. Now here you can see that a knee is flexed. Now how do we calculate the instantaneous center of rotation of this femoral condyle of this joint? Okay. Now here you can see we actually, what is required, I can go back also to that figure. What we actually do, we consider movement of the points in the range of 10 degrees. So suppose we take a photograph and locate a marker or locate a point for say 80 degrees knee flexion. The same point, the displacement of the same point is located in another figure or photo or digital X-ray or precision sort of imaging corresponding to 90 degrees flexion. So this increase from 80 to 90, 10 degree step, we actually locate, say for instance, the movement of this point, as I show it with my arrowhead, to this point. Okay. Similarly, it is not too much visible here in this photo. We actually locate the movement of 2 points corresponding to, in another location, 2 points from 80 to 90. Now what we do is join these 2 points by a line at the corresponding set of points, and then we drop the perpendiculars from this line joining the 2 points, and the point at which these perpendiculars actually bisect or meet is the instantaneous center of rotation between 80 degrees flexion to 90 degrees flexion. Okay, this range, 10 degrees range. So if you actually go on calculating for these 10 degree steps, you will end up in finding the locus of this instantaneous center of the femoral condyles during flexion extension. So this is basically a semicircle, as you can see here from the figure, that the instantaneous center of rotation of this femoral condyle is actually changing from in the range of 10 degrees from one point to the other. So obviously, when the instantaneous center of rotation changes, the lever arm of the muscles corresponding to that posture would change, and thereby it will change the quantitative value of the moment around that point. Now, if I go, as I was showing you, another picture where we calculate the instantaneous center of rotation here. So here it is tracking the patella. So the patellar movement, as you can see here, very easily 2 points on the patella. So we join the 2 points and drop perpendicular. We join the 2 points, drop perpendicular. So this is the instantaneous center of rotation of the patella for 10 degrees. So if you read the book further, then you can understand clearly that how this is calculated. Now let us come to the slide. Before I move on to some problems, I'll just try to explain you that the role of the patella. There is some questions already. Oops. Oops, just a moment. Yeah. So now you can ask me some questions.
Sir, the process by which you find the instantaneous center of rotation, like you have done for 10 degrees, but I guess that instantaneous center of rotation might be changing continuously, right?
Yeah, of course. So it is like they are considering 10 degrees. Say a point 80 degrees moves to another point within this 10-degree increase in flexion. Okay. So based on the movements of these points through 10 degrees, they are calculating the instantaneous center of rotation.
So,
Okay.
so for the first step, you mark a point on the patella bone, and after 10 degrees, you take the same point and you
Yes,
try.
yes, yes, yes. So
So,
you have
but
to take,
how do the other perpendicular came in? Like for
no,
those
no,
2 points, we can connect them and do a perpendicular bisector of that. But
yes.
we need
But
two
you have to
lines for
take 2
intersection.
points. No, you need 2 points. You will probably notice, you look into the book, they are considering 2 points.
Okay. So for those 2 points, they track the position after 10 degree, and for those 2 points, they connect line and do perpendicular
Yeah,
bisector. Okay.
because otherwise you cannot get a bisector. The perpendicular
Yeah, right.
bisector has to.
Yeah.
Yeah. Okay. Now I move to the patella. I don't have too much time, so this is also a very important mechanics from mechanics point of view. But this book, as I told you, is very nicely written book. Okay. So if you read it, simple language, very lucidly written, good for the starters who are trying to learn the principles of biomechanics. Okay, so it bridges very nicely the knowledge of, say, anatomy, physiology, and the basic engineering mechanics. Okay, it's good for the starters. Now let me move on with the lecture. Now, I think these slides are very clear for you to understand. This is a side view. As you can see, we have the tibia, we have the femur, and we have the patella. Now, patella is held together or pressed inside from the anterior side by the tendons, which is the quadriceps femoris tendons. So, quadriceps tendon, which actually is attached to the quadriceps muscle on the one side. On the other side, just a moment. Oh, sorry. Slide pointer. Yeah. So this is the quadriceps tendon on the one side. The other side is there is this patella ligament. Okay. So these two actually hold the patella in place from the front, from the anterior side. You can feel yourself that the kneecap or the patella is being pressed inside the knee joint, and this together actually forms the knee joint. So we have a connection between the patella and the femur, giving rise to patellofemoral joint, and we have the primary joint between the femur and the tibia, that is called the tibiofemoral joint. Okay. Now it's very interesting to note the role of this patella. Okay. Now, as you can see, when you flex and extend your knee, the position of the patella with respect to the knee joint actually changes drastically. Okay? It is actually swiveling over. So during flexion, you can see here during flexion, how the position of the patella is going inside the groove. Okay? You can see here. You can consider from one side, if you move from the left, as I am pointing, left figure, say this figure as position 1, and this figure on the right as position 2, then the knee is being flexed. So during flexion, you can see the patella is moving inside the groove. Whereas if you reverse it, see, if the right becomes 1 and the left becomes 2, then the position of the patella, you can see, note very clearly that it is being displaced anteriorly. It comes up and it increases the moment arm. Okay? It increases the moment arm with respect to the joint center. Okay? So here, if you can see the picture towards the left as I am pointing out, so you have the quadriceps femoris tendon on one side, a line of force. You have the patella ligament, another line of force. So the resultant should actually pass through the instantaneous center. Okay, and this, with knee flexion and extension, this moment arm is actually varying. The D1 is actually varying. In case of, I will say what happens if there is a problem with the patella, but before that, I will just show you a figure from the book. Just a moment. Where is it? Not much time is left. Just a moment, I'm searching for that. Yeah. So if you look here very clearly, as you flex or from flexion to extension, when you straighten up your knee, the patella actually displaces anteriorly, thereby increasing the moment arm of the quadriceps tendon and the ligament. So this results in more reactive movements as well as for the knee joint. So if you are looking into the functions of the knee joint, so there are two most important functions that you can see here, functions of the patella. The two most important biomechanical functions of the patella is, the first is it aids knee extension by producing anterior displacement of the quadriceps tendon. So it basically aids knee extension. During knee flexion, the patella is goes inside the groove. It is rather the moment arm is decreasing, but in case of knee extension, it actually aids by increasing the moment arm. So by producing anterior displacement of the quadriceps tendon throughout the entire range of motion, thereby lengthening the lever arm of the quadriceps muscle forces. Now, since it shares a joint with the femur, so it also distributes the forces in a wider area, leading to a wider distribution of compressive stresses on the femur by increasing the area of contact between the patellar tendon and the femur. So Due to its presence, it actually helps to distribute the compressive forces in form of stresses in the patellofemoral joint. Okay, so these are the two main functions of the patella. Now, if the patella is removed, what happens is a clear picture is figure 7.20, the second picture after patelloctomy. So you can see very easily what is the difference. So during flexion, the displacement of the patella is not present here in this lower picture. Okay? I think we have to end the class here. You can have very quick questions. I will continue tomorrow in the next class. Hello? Can you all hear me?
Sir, I
Yes,
couldn't understand a few parts that you explained. So, like in
which
my
part?
understanding, patella glides on a bone, and the curvature of that bone is different. So, in the extension position, there is a large momentum. Uh,
Yes.
so the line of action force is
As
reduced.
you extend, just a moment. As you extend, yeah,
Hello.
yeah. Please carry on.
So the role of patella is to increase the momentum so that by applying less force we can achieve large moment for knee, right?
Yes, during the extension, during knee extension, it only comes into action during knee extension. Okay.
And it has no role to play in flexion.
No, it idles. It's like a cam in mechanical engineering. You people all have know the function of a cam.
Yes, sir.
How is a cam profile designed? Okay. Does it always do some job? It also idles during
Yes,
certain.
yes, yes.
It's something comparable to that. So during flexion, it goes inside the groove. So between the femoral condyle, there's a groove.
Yes,
Okay.
yes.
It goes inside the groove. But when you are extending the knee, the opposite movement, it actually comes out of the groove and increases the momentum anteriorly. It displaces more towards front, thereby increasing the tension in it increases the tension in the quadricep and the ligament attached also, apart from increasing the momentum.
Okay.
Because it laxes. Once it goes into the groove, when during flexion, once it goes into the groove, these quadricep tendon and ligaments, they slack.
Yes.
So it's a very complex system. You see, just a reverse movement, this idles, and another movement, say extension, it has a primary function of stabilizing the knee.
So during the knee flexion, there are
Mhm.
certain group of muscles which are providing
Of
like
course.
contra moment due to, so they are counteracting
Yes.
to the weight of the knee. So
Yes.
that is a separate muscle group force
Yes.
apart from these tendons and ligaments, right?
Yeah.
Okay.
Exactly. So we'll continue that simple calculation, and then you get an idea of how. First we will do static analysis, then we will move to dynamic analysis. But dynamic analysis we will consider extensively in case of a hip joint. Okay, all the calculations, things like that, inverse dynamics things, taking the case of a hip joint later on. But you can apply the same in case of a knee joint, the same principle. Okay. Okay. Thank you, everybody. Just a moment. Why can't I download? Anyway, ठीक है. I'll see you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.